So I was like,
Just the last question.
I still asked my question, but I was a little more cautious. If you're a CS, so it's basically he was like, yeah, you're a CS, you should be able to explain this topic to them, whatever, yada yada. And then the other guy, we himself, he was all the really good
Georgie. Are you done with this?
No. So,
Maybe specify what you want that sort of like I was getting like 15. You could just like ask me all those things you want to but if you don't think there's something they also mentioned that I think with REST there's like a default like scroll/API. I don't know if they can it's just taking time away. I mean, for this, I already that's for every time I talk to you, it's just like, I just been coding for the last 10 hours. I don't really can do it. I'll go talk a lot. I mean, yeah, you guys go. What do you guys
But anyways, I didn't know that because Johnny was not Johnny, and I've been in the group chat for like a few weeks. It's like the answer.
They always talk about, hey, generally want to talk about.
I don't even think Alex knows anything.
And look forward to your best. It's like 2 years.
Okay. Let's get started. So I guess there's a football game. Is that why it's so crowded out there?
Yes. Terrible.
Who they played today? I don't even know.
Weaver State.
Weaver State?
Mm-hmm.
Utah plays Weaver State still?
Yep, this is the first of one of the season.
I see. So you just want to beat up on somebody first and then... let's see. Just trying to do like this business here. So homework 1 went out. Has anybody given that a shot yet?
Took a look.
Took a look. How is collaboratory working?
Really well.
It's working well. It's surprisingly good, huh? And you probably noticed that there's nothing of like using GPUs in this assignment. That's not a mistake. It's all NumPy. I think I mentioned this last time. So yeah, but the next homework assignments will all be using GPUs, and again, laboratory should just work. Any questions on homework? Anybody have any not like super detailed ones, but just like general questions?
This is for way in the future, but when we turn it in, do you want us to turn it in a zip file or just the individual notebooks?
Well, I guess it doesn't matter, but I just do the individual notebooks.
Okay.
Yeah. Probably that's the easiest. Yeah, I'll ask the creator. Tommy, what do you think?
I think individual notebooks are
Okay,
better.
individual notebooks. Okay. All right, cool. Other questions? All right, well, let's pick up where we left off last time. So, let's see. These go on. Okay, so we were talking about different loss functions. These loss functions were these functions that told us like how well we were doing at predicting in a classifier, predicting the correct class. So we looked at the support vector machine loss. Those are a hinge loss or a margin loss, and then we started looking at softmax. So these are the two most common loss functions you'll see when working on classification problems. And a lot of machine learning is classification, it turns out. I mean, I don't know, I guess you could also say a lot of it's regression. A lot of it's everything, I guess, but yeah, you'll see these loss functions all the time. So we were kind of at this point where we were saying, okay, like, you know, we have this new function, the softmax function, that turns the scores that our linear classifier gives to our data point x. It's gonna, you know, there's so in the case we've been looking at, there's 10 examples, or actually in the simpler ones, there's been 3 examples. Cat, car, frog here, but our linear classifier gives a score to each one of those, and then our softmax, through a couple of different transformations, turns them into a probability distribution. And what we were saying at the end of last time was like, okay, in this case, we actually want to compare it with another probability distribution, like the one that's got all its probability concentrated at the correct class. But before we did that, we sort of thought of like another way we could have done this, which was to turn this into a positive number and tried our very best to a positive between 0 and infinity, and try our very best to work with that. So this is what we call the maximum likelihood estimation. I quickly passed by it, but we're going to come back to it here in just a couple of slides. I just want to start here again. What we said was like, okay, well actually really what we want to do is we want to compare these two distributions. Like our current model is giving us these probabilities of being either cat, car, or frog. What we really want it to be is that. So we want to have some way of measuring the difference between those things. And we start talking about ways of measuring the difference between distributions. And so we've talked a little bit about this KL divergence. And it ends up being a nice way to compare distributions, but it has some sorts of problems associated with it. One of which is the fact that, like, it's got a Q, it's got some stuff in the denominator that might be 0, that could be a problem, and it's not symmetric, and I don't know, just things like that. It turns out there's actually a related term that we end up working, sinister looking man over there. How many bits does something require to be encoded? And we're not going to go through that, but the ideas are there, and if the logs are always correspond to log base 2, then actually we're talking about like expected bits per, or not per, but expected bits for like encoding messages within like a system described by this probability distribution. But it's okay. If you don't know anything about that, let's just talk about entropy. So entropy is a way of measuring something about like the disorder or like the surprise of distribution. And it's defined in this way. And it looks maybe kind of funny. You have a sum with a p in front there over all the probabilities in the distribution. That always corresponds to an expectation. So this is an expectation of something. Well, what is it? It's the log of p itself. And this does have, again, some notion of like the length of, like, again, the number of bits required to encode messages, but it's the expectation of something in this distribution. But this function has really nice properties for thinking. So for one thing, the entropy is always non-negative for any distribution, and you can see that. I mean, these are all non-negative, and then the log of p is a value between 0 and 1 that's negative, but then we have a negative sign out in front to makes it positive. So these are always non-negative. I don't know if that's super important, but it's kind of nice. But what's really nice is that they're at the boundary at 0. It's only 0 if your distribution is a Dirac delta, which what that means is it's one of these distributions where all the probability is concentrated at one of the classes. So in this case, class K. But it's zeros everywhere, and then all the probability 1 at the class K. So that just means like we're totally certain about this. There's no probability, or there's probability, but it's all concentrated in one place. So it's like we're totally certain about what's going on here. So this Dirac delta thing will come up again. But that's interesting, right? So like, think of like entropy. If you study physics, it's something about like disorder. So when our distribution is like as undisordered as it can be, it's all concentrated in one place. You're certain about something, then you get entropy 0. So that's kind of interesting. Another way to think about that is in terms of surprise. So like, if you're drawing from this distribution, you always draw the same class because all the probabilities are concentrated there. So there's no surprise when you pull something, when you draw from this distribution. So I like to think of entropy sometimes as surprise. It helps to think about what's going on. Here's another interesting fact. The gradient, so all the partial derivatives of this function with respect to all the entries, it's non-positive. So this is a concave function, looking downwards. And the gradient is 0 if and only if the probability is uniformly distributed over all the classes. So gradient equals 0 means you're at a point of, so in a concave function, you're at a maximum of this function. Which turns out there's only one maximum. It's at this distribution right here. By the way, the domain here and everything I'm talking about are probability distributions. So, again, these sequences of numbers that are all non-negative and sum to 1. So anyways, so this thing has a max at the uniform distribution. So the entropy is greatest at the uniform distribution. So your surprise is greatest at the uniform distribution. When you draw from here, you have an equal probability of drawing any class. So you're most surprised when you draw this way, yeah.
So is n displaced the number of classes?
Yeah,
Okay.
right. So, right, the same n as up there in that cell.
Right.
Yeah, thanks for pointing that out. Okay, so that's interesting. That's a really nice property. Okay, so great. We have some way of sort of measuring like how disordered or ordered a distribution is. Then we had talked about this other thing the other day, this KL divergence. It's defined like this. It looks pretty similar to entropy, except that it's got a couple things different. One is it's got another distribution involved, and its probabilities show up in the denominator. And there's also not a negative value there, although if you were to use the properties of log and separate that log of p over q into log of p minus log of q, I guess there would be, in one of those terms, there would be a negative sign. But anyways, it's kind of got something, it's got a very similar look. It sort of like, when you look at it just like this, it's like totally unmotivated, like what is this thing? I'm going to mention a few properties about it that are really nice. One is that it's always non-negative. And guess what? It is 0 if and only if the two distributions are equal, and because there's a probability, it's always almost everywhere. You know what almost everywhere means in probability? So it's like on events that would never happen, they have probability 0, they could maybe be different, but they're basically, and with finite distributions, it actually doesn't mean anything. It just means that all your probabilities are actually equal to each other. So it's some measure of difference between them. Now, we talked about the fact that it actually isn't a distance between distributions because, like, for one thing, it's not symmetric in P and Q. If you swap those, you get a totally different answer, unless P and Q are the same, in which case you get 0. So that's kind of nice. Like, in some way, measuring like the difference between them. So it's always non-negative, and 0 if and only if we have exactly the same distribution. Okay, so that would be great, except that it has some undesirable properties. So there's a very related term, related to both these here, measure called cross entropy between two distributions, P and Q. So this looks a lot like the original entropy, except that instead of it being this expectation over the negative log of P, it's this expectation of negative log of the other distribution. And it also has some sort of like information theoretic interpretation. It's where like entropy is something about like how many bits encoded in this one system. It's like how many bits for these messages coming from P that were encoded using Q. But the important thing is if we do a couple manipulations here, we actually can turn this into something recognizable and you'll see very useful. So, so just some quick manipulations here. This is equal to this because all it does is add and subtract the same value over here. Those things look like the entropy and negative entropy up above. That's exactly right. That was done on purpose. If we take the entropy term, the one from the very right, bring it over here to the left, and then take what's left over, they both have a P here in these coefficients here in the sums. And then we just use properties of logs to put all these terms together. We get something that looks like this. And if we look at this, we see that this is the entropy of P, and the other term is the KL divergence. So this is actually where KL divergence comes from in the first place. So what do we have here? We have the cross entropy term. So this way of sort of measuring, like again, something about bits and encodings with different systems, just corresponds to these other two terms that make it a bit simpler to think about. So again, this is a comparison between distributions. A couple of properties here that are really important. The cross entropy is always greater than the entropy of P. The cross entropy between P and Q here is always greater than or equal to the entropy of P. And that's because this term right here, the KL divergence is always non-negative. And we also know that's always greater than or equal to 0. So we have another one of these things that's always greater than or equal to 0, but it has like an additional lower bound, maybe sharper than just 0. And this really interesting property. So again, if we take this Dirac delta distribution, so again, all the probability concentrated at K, and we look at the cross entropy between that and Q, what we can do is, oh, this should be, sorry, this should not, this is an equal sign. I need to fix that. This is an equal sign. This is equal to this, just by following the definition. Okay. What is the entropy of the Dirac delta? We already talked about this. This is 0. Now, what's the Hale divergence of this distribution with this Dirac delta function? Well, if we follow through here, what we see is everywhere that, oh, that, whoops, that should be K. Bad slide. Imagine this is a K. So, let's see, looking back at this term right here, Q, or sorry, P in this case is zeros everywhere. So yeah, this is an interesting point, and I should maybe point it out here, but 0 times log of 0 we take to be 0. It's one of those like, was that L'Hopital's rule things? You can look at the limit of like the entries going to 0. You know, you take P, take this value and this value, you take the limit as you go to 0 from the right, you actually go to 0. Remember that from first semester calculus a long time ago. Anyways, so what happens is like those are all 0, and then the one term where your Dirac is a 1, you get a 1 there and a 1 there, so a 1 there and a 1 there, and you have your Q left over, which that should be QK. And then I just use the properties of logs to flip this over and have them find a sign up front. So when I look at the cross entropy with the Dirac delta, I just get that minus log Q, and that's actually the maximum likelihood estimate again. So that cross entropy term, actually, when you cross it with one of these Dirac delta distributions, which this thing in purple really is, you actually just get right back to that. So maximum likelihood estimates show up all over the place in machine learning, and here it is again coming in kind of through a strange back door that we weren't maybe expecting. But if we compare two distributions where one is the Dirac delta, then the term we get right here is this maximum likelihood estimate. Just minus log of the probability of the class, that's correct. Okay, questions about that?
I have a question on the last slide.
I'm assuming you mean all of them.
Yes, if all the delta k's are 0, why is it? Because 0 times the log.
What's that? This term right here?
The KL.
This?
Yes.
So this is not 0, this is this.
Okay.
The entropy of the Dirac delta is 0. There's no surprise when drawing from a Dirac delta. You always get class K. And then I'm just using the definition up here and taking the fact that 0 times log 0 is 0. That's all. Other questions about this? If you were for some reason writing notes because you believe that I'll never put the slides up on, which that's a pretty decent belief at this point. A long weekend is coming up. I'm going to fix all of that. That should be an equal sign, and that should be a K. Any more questions? Okay. So you compare these two things. Great. Everything's turning out great. These are simple things to look at. So this is putting it all together. Our loss in the case of a softmax looks like this. We have we take our probability distribution and we transform it to something like this. Our scores are these. So transform, we take the negative log of that, and that's our loss. That's our measure of how different we are from the right answer. Okay, so a bunch of questions. So what are the minimum and maximum values of this loss? If you could go back to that slide, you could sort of think about it, but because it's just cross entropy with a direct delta. What's the minimum value of this loss?
0.
The minimum value is 0. Good. What's the maximum value?
There is no max. It just keeps going.
Yeah, it's unbounded. But again, the important thing here is this loss is, like in the SVM case, non-negative. So when we try to minimize the loss or the cost that we've incurred through our current model, we're pushing everything towards 0. Okay.
I have a quick question.
Yeah, please.
Sorry, you just said, like in the SVM case, is that the hinge one?
Yeah.
Okay.
Yep. At initialization, so like we randomly initialize all of our parameters, and what usually happens then is that, like, because there's no reason for the initialization to prefer any of the classes, usually you'll have all the scores being equal. So if all the scores are equal, what is the loss? Who said it? Who wants to be brave and admit that they said N?
It's got to be a maximum value.
There's no maximum value, right? We just said that there's no maximum value.
Yeah.
But someone said N, and they're right, even though they don't want to admit it. It's N, right? Because what's happening over here? If all the scores are equal, then all these exponentials in this are all the same. So I could basically like factor them all out, right? So they would cancel, and I'd have a 1 over the sum of 1s, and there's n classes here, so I have a 1 over n. Now it's the log, so I have log of n. So the answer is log of n, not n, but whoever said it and doesn't want to admit it, they were right. Good job. Yeah, the answer is, oh, here it says C. Whoops. So in our case, when we have like 10 classes, like in C410, the maximum will be that. That's like, or not the maximum. That's what we. That's what random is. And typically, like knowing what random looks like is really important in these. This is typically what you compare against. You're never going to see like the maximum. Like you're not going to have things that like blow up to infinity. Usually, you can make it happen, but you're not usually going to have that. What you're usually competing with is you're trying to see that you're learning something. If what's happening is you're assigning everything. If your current model is basically like producing a loss that is the random loss, you haven't learned a thing, right? There's no, unless like there's all like the only structure in your data is random, and then in which case this is a bad machine learning problem. But you're usually always comparing against what the random loss looks like. That's the thing that you're looking at. That's the thing that you care about. And if you can see that, you can typically tell that you're not learning anything because like your loss just remains at the random level. So, anyways, pro tip. So we learned about softmax, and we learned about the support vector machine SVM. Pretty similar to each other in terms of like what they're trying to do, but they just do it in different ways. The SVM is trying to push the score of the correct class to be larger by some margin than any of the other classes. And entropy, the cross-entropy loss, the softmax loss, that is trying to increase the probability of the correct class to 1, which at the same time is pushing down the probability in all the incorrect classes, since this is a probability distribution and everything's a sum to 1. So yeah, so like, when would you choose one over the other? And they are. How beautiful they are. When would you choose one over the other?
Softmax.
You're a softmax guy. Okay. This isn't even like a no decision, just like, or no like thinking about a particular problem. Just like, always softmax. That's pretty typical actually. Softmax is used all the time actually in favor of the support vector machine loss. Any thoughts on why that might be?
The change is gradual in case of softmax, whereas in case of this SV, there is a sharp drop. If there is a difference by 1, so at the hinge point, after that, it all gets to 0. But so there is a sharp transition from 0, and then we just simply.
Yeah, that's right. There's a sharp transition. So like, yeah, so I think maybe what something you're getting at is once you have scores for a particular class that make it 0 for that class, then or for that problem, I'm sorry, then or that point, then like there's basically no contribution like left to changing that. It's just like it could be a whole bunch of different values, and it would still get like a 0 loss. And there's something kind of strange about that because like shouldn't it pick out like one of the values? But again, like once you're over this threshold, you could continue to increase the score of the correct class, and it would just stay 0, and you know. So it's kind of a funny thing that happens. It's not bad, but it's also kind of funny.
Can you talk about differentiability?
Yeah, they're both differentiable. Except that the hinge loss has one point where it's not differentiable when at 0, or when sy is equal to sj plus 1. Yeah, that's kind of looking forward a little bit to what we're doing next. Like maybe there's some people here who are like knowing that we're going to have to be taking derivatives of everything here soon, and they're looking at that and they're like, that's not good. That's not good. I can't differentiate that. Well, it's actually not so bad, right? Because while the derivative is discontinuous there, the function still is continuous. And if you think about it, you have a 0. You have a probability of 0. Let me say it differently. The probability of actually having a 0 on the right-hand side there is 0, because your two values s, y, and sj are real numbers, and the probability of picking out any particular real number within an interval is 0. And in practice, it never happens, but it could happen. In which case, you just decide if it's going to be, the derivative is going to be, I guess in this case, let's see, -1, or it's going to be 0. It doesn't really matter what it is there. Yeah, so like what we're going to be doing is something called gradient descent, and we'll be talking about here in just a few minutes. And it requires us to do derivatives, and you might see stuff like this, and you go, darn it, that doesn't look good, and I can't differentiate it. And in fact, you maybe know something already about what are known as Rayleigh's rectified linear units, which is like the preferred nonlinear activation that's used in neural networks, modern neural networks. And it also has, it's exactly the same function. That's basically, it's a max of 0 and and the score. And so it has the same problem, but the good news is that if it's not differentiable only at a few finite number of points, we don't even have to worry about it. It's never a practical problem. So, but yeah, but you might also say like, hey, I would like to have everything be differentiable, so I'll use the softmax, and that's great. There's really no theoretical reason why you ought to use one over the other. It's just that there's a lot of preference for softmax, and that's probably because there's always a gradient, there's always a non-zero gradient there, and that allows you to continue to keep learning in one of these gradient-based learning algorithms. But it can be so small when it saturates, near like large probabilities or whatever, that it almost has the same sort of problems as that. The other thing is, softmax really only works well when you have a small number of classes. And this small number of classes is maybe like thousands of classes. So that doesn't seem very small, but thousands of classes. But if it starts to be very large, like tens of thousands of classes or something like that, then softmax becomes really bad because basically like there's probability is getting stretched out over so many classes that you never really like differentiate from like being uniform, being random. And so actually what happens in those cases, you can still do classification. You just use you use a loss that's related to the hinge loss. It's basically like a couple of hinge losses that work together to like take examples from the similar class and make their scores close to each other, and take examples from different classes and make their scores far apart from each other. And those are called Siamese loss or triplet loss losses, and we'll actually be talking about those later in class because they're pretty useful in the case where you have a lot of classes. Okay, one last question here. Suppose I take a data point and I jiggle it a bit, changing its score slightly. What happens to the loss in both of these cases? So here are our scores. For 3 different examples, we're assuming they're all like we're assuming this is yeah, well it says right here the class is 0 here, so we look at the 0th term, and this is the highest score. So in either case, we're going to assign the correct value or the correct class to this data point. So what happens in this first case if in the softmax, if I jiggle, so to speak, if I just change the scores just a tiny bit so that these are, like this score is maybe a little bit larger, a little bit smaller. And let's just look at this case real quick. What happens in the softmax? The correct class is 10. It's at something, it's at some loss right now. What happens if I increase it a little bit? What happens to the loss? So the loss decreases a little bit. Why does it decrease a little bit? So first of all, don't think about the math. Why does it decrease a little bit?
There's separation between.
Because you're assigning a higher score to the correct class, and what this does up here is it increases or decreases with those kinds of changes. So the loss, remember, is a measure of how different we are from the Dirac delta distribution. So if we increase the score, you can think about the denominator. So the numerator and the denominator both have a term e to the SYI. That's the score for the correct class. They both increase by the same amount, but this denominator also has some other stuff there. So that term is getting closer to what? Well, not infinity, because the denominator is always bigger. But if let's say the score increases by a lot, what is that getting closer to? 1. Good. It's getting closer to 1. And that's the case. As you increase the score on the correct class, that probability for the correct class is getting closer to 1. That means that minus log of that is getting closer to 0. Good. And that's true for all of these on the softmax case. And vice versa, if I were to decrease it a little bit, that ratio would actually decrease between the top, the numerator and the denominator. I get a lower probability, I get a higher loss. So softmax is nice. It's sort of responsive to these changes. Okay? What happens to the SVM in these cases? Let's start with this one right here. So it's kind of hard to do, but if I put -2 in for SJ or -10 plus 1, I get a negative number. That's 0. If I change, that's for this. When j is equal to 1, when j is equal to 2, then the same sort of thing happens here. 10 still swamps that out, right? So I get a 0 there. And if I change 10 by a little bit up or down, does that change? Does that change any of those max terms in there? No, because they're pretty negative, right? And even though changing this down a little bit would make that less negative, it still is not enough to push it over 0. The same holds with this case right here. These scores are so low that that still say 0. But what about in this case when we're at this balance point, which actually in reality you would never get to, as we were just arguing. But let's say you were there. What happens in this case? If you increase it, so at this point right here, what's the loss? 0. Each of the terms contributes a 0. Let's say I increase my score by a little bit for the correct class. What happens? That thing, 0, because I'm subtracting it on. But if I decrease it by a little bit, if my score becomes a little less sure, then all of a sudden I get non-zero. I get a positive number there, and all of a sudden there's some loss. And this is what I was saying earlier. This is kind of a strange loss because all of a sudden make a small change and then boom, all of a sudden you've got something, even though maybe that shouldn't matter enough. But it just it depends on the margin. And this is another reason why people often will just use softmax and not the SVM loss. And that's because you have this hyperparameter. It's been 1 the whole time here because I'm using existing slides and they all have a 1 in there. But you can imagine that being just some parameter delta. We could pick it to be anything. It could be 1, 10, 1,000, million, whatever. The point is that we have to pick it. We have to pick something. And anytime you have to pick something, there's like a whole host of things that become an issue. Now you could argue, well, you're picking between the two losses anyways, and that's right. You're making decisions all along the way, but at least if you know Occam's razor, you're kind of like a Occam disciple, you might just be like, get rid of hyperparameters as much as possible. Anyways, the point is that most of deep learning is like art rather than a science, and here's one of the artistic pieces. You get to pick a loss function. Okay, so with that, kind of done just talking about these losses. The reason why we spend so much time on this is that we're going to see these losses over and over and over and over again. If we're doing classification, I promise you, there's going to be either this or this. And there's going to be a this if it's like a small number of classes, which means thousands. And it's going to be a this if there's like a huge number of classes. And it's not just this when it's a huge number of classes. It's actually like a bunch of these huge losses working together. So yeah, they're super important. And then also remember, we also talked a bit about regularization. So at the same time that you're measuring how different you are from the actual answers with your loss function, you also have an opportunity to penalize or reward, as the discussion was last time, certain configurations of the weights. And some of the simple things that we looked at were like, things that make the weights small or sparse or whatever. Okay, so the next thing we need to talk about is how do we find the best W? How do we actually find the weights, the parameters that make this loss small? For that, I've got to switch over to the next slide deck. Okay, so basic optimization. All right, so what's the point of loss functions? Well, loss functions, as we just described, we were saying that they tell something about how different what we're predicting is from the actual answer. That gives us an entire surface of losses. It can be really simple, like this top surface, some sort of like quadratic looking thing. That's a really nice, if you ever get something like this, then you're in business, because this is a convex problem, super simple to solve by gradient descent, no problem. You can find the global, it's It's easy to prove. You can find the global minimum always. And it used to be that people only ever like went after convex problems or like a small class of non-convex problems that you can understand really well. And then deep learning came along, and you got lots of surfaces that look like this. Well, neural networks came along. It's not really just a thing of deep learning. It's just like neural networks themselves. So first of all, I'm showing like parameter space as being like 2 dimensions. Like that's definitely not the case with neural networks, especially deep neural networks. They have millions of parameters. So you got to think of like this surface describing the loss for every configuration of parameters. And if you know, like a very standard convolutional neural network that's used for so many different tasks is called a resonant, a residual network, and a resonant 50. That refers to the number of layers in the network. A resonant 50 has 25 million-ish trainable parameters. So the loss surface is living in 25 million dimensional space. I don't know what it looks like. I have no clue, but I imagine it looks a lot like this. There's 25 dimensional peaks and valleys, and there's a whole bunch of places to get to you know, deep places to fall into, and you know, I don't know. It boggles the mind to think about it. And yet that's what's happening here, is that this loss surface is parameterized by our parameters, the parameters of our model, the weights in our model. And they are huge. We're like in your homework you'll be working with like some smaller neural networks, but even those have like hundreds of parameters. I don't know what loss functions look like in 100-dimensional space. But it doesn't matter too much because we can still go after these things and just sort of hope for the best. And this is actually one of the still like not very well understood, very not well understood things about neural networks is that despite, what we're going to do next is talk about how to like find these minima. In the convex problem, you have the global minimum, and you can go right to it by just walking downhill. If you use the same procedure in something like this, great, you'll still walk downhill. It's just that you might not end up at the global minimum, right? Like, if you start over here, then you walk down, you might end up like, I don't know, it's hard to tell exactly what's happening here, but you might end up down here. But really, like, this one over here is lower. But you didn't get there because, you know, you were over here. And if you started over here, maybe you'd get to the one that was deeper. But you didn't, you know, you just don't know that beforehand. And so these are the kind of loss surfaces that we're going to be like living on. Like those very simple softmax loss or SVM loss, they're going to give us crazy looking loss surfaces like this. And we're going to be trying to optimize the loss, which in this case means minimize the loss as best we can. And you might think like this is hopeless, and yet what is the case in deep learning, especially when you have lots of parameters, is that you're training the way that we do the gradient descent or the walking down the hill. That actually ends up like every time finding a different minimum that is equivalent in some sense, like in terms of like loss, like the same amount of loss as any other time that you initialize the parameters and do it. It's like this phenomenon that everybody observes. You'll observe it probably if you know, well, hopefully you get some in the homework, but you know, when you're working on your own problem and you train, like the project that we'll do at the end of the semester, or that you'll do at the end of the semester. I said you'll do it. You're going to find that you'll train this thing many times, and what's very likely to happen is you're going to find a minimum, and it's going to be different. It's going to be different configuration. It won't be the same exact parameters, and yet the loss will be basically the same as the other time you train it. And it's bizarre. Everybody observes it. There's some attempts at explaining like why this would be through thinking about symmetries in the loss and things like that, but no one really has a good explanation for it yet. It's a combination of symmetries in the loss space itself, plus the inductive bias of stochastic gradient descent, which is what we use to train these things. So let's get there. I don't know anything more about it than that. Just having read a couple papers on it, it's really fascinating. But this phenomenon you'll observe, and what's cool about it is whatever so even though all these losses are equivalent, we have no idea if there's a global minimum. The configuration of parameters that we find there solve these amazing problems. like the first lecture, we talked about all these cool things that are being done with deep learning. The losses, or the minima that are being found in these loss surfaces produce models that are doing these great things. So it's sort of surprising. It sort of flies in the face of most optimization theory, and yet here we are. You're all excited to take this course on deep learning for some reason because it works. Okay, so just to kind of warm up, one thing that you could do in a crazy surface like this is to just like randomly search, right? Just like sample points, sample parameters from your, whatever dimensional space. So with our with our linear models on CFAR10, with a single, just a single linear model, we had a matrix of 10 rows in 3,072 columns. So that's what is that? 30,720 parameters. So that's already this huge dimensional space. And we had a bias vectors too, so that adds another 10. Anyways, we're already in a really high dimensional space. So if you just sort of sampled, randomly, uniformly from vectors of length, or distributions that produce vectors of length 30,720 plus 10, 30, yeah, that's right. Then you could just like test the loss each time, and you can look at the loss, and like next time you sample it, if it's lower, you say, okay, great, like this set of parameters is better. And you can do it again if it's not better, then you say, oh, you throw it out, don't worry about it. You could do this. It sort of would work. But there's a massive problem with it. And what is it?
We're not exploiting any information about what direction we should go.
Yeah, exactly. That's exactly it. The loss function tells us something about where to look, and in random search, you're not using that at all. Is that what you're saying?
I was going to say maybe backpropagation.
Yeah, well, that's where we're going. But that's right. So like, the problem with the random search is that it's not using any information that the loss function is telling us, local or global. It's just sort of trying things, and I guess you could sort of like make random search be kind of taking information. Like if you start to see that there's losses are lower in a certain region, and you might start sampling over there. But it's way slow, and it's compared to like doing gradient descent, it's way slow. And usually, if you try to do this in a reasonable amount of time, then you don't even get great accuracy. So like in CFAR10, where if you can do really really well, like over 95% accuracy, if you run this for a reasonable amount of time, you only get about 15% accuracy on that. So like, it's just a terrible way to go. So here's what we really are doing. We're on this amazing loss surface. It's probably in the Alps someplace, or who knows. But like was pointed out, what we want to do is want to use local information about like where we are to decide where to go, where to sample next, essentially. And the way we do that is we're looking for minima in our particular problem. You could be looking for maxima, in which case everything that I'm saying next will just be reversed. But you were looking for minima, so you want to go downhill. Whatever downhill looks like in 25 million dimensions, you want to go down. So how do you do that? Well, you've been studying it probably since high school, maybe since college, I don't know, maybe since elementary school for some of your geniuses. Calculus. I mean, this is like what calculus is meant for. It tells you locally in which directions, like wherever you are standing right now, it tells you the slope in all the different directions around you. And it's a super simple idea, and yet it's super, super powerful. So just as a brief review for anybody who's not done it in a while, you probably saw this when you did Calculus 1, and maybe you did multivariate calculus, where you looked at something called the gradient. So a multi-dimensional vector function, then you might have something called the gradient, in which case you're thinking about not just the change in your function in one direction, but change in all the directions. So like this sort of like limit thing that defines a a derivative, you just sort of do it along each of the axes in your space. And that's telling you the slope in each of those directions. And it turns out that the gradient tells you the direction, wherever you are standing and however many dimensions you're standing, it tells you the direction of steepest ascent. Steepest ascent from where you are, just locally. So it's like, you know, I'm standing on this flat surface, so that's not very good. But if I was standing on the slope over here, it would point, and if I'm right here and I take the derivative of this surface, it points me that direction, because that's this direction of steepest ascent. I might actually put a little bit more like that, I don't know. Hard to tell. But the point is that like, that's what it does. Now, your surface could be like really crazy and curve a ton, like all the time. And so that direction of steepest ascent might only apply for a short amount of time, or a short amount of distance or space. But yet, locally, right next to you, it is the direction that you should go if you want to climb uphill. However, we don't want to find maximum, we want to find minimum. So we want to go in the opposite direction. So we calculate this gradient. Actually, I want to go in the direction of steepest descent, which actually ends up being in the opposite direction. So the negative of the gradient gives us the direction of steepest descent from wherever we are locally. So, you know, like in practice, the way this works is not really like this, actually. Loss functions could be super difficult to think about and to compute derivatives of, in which case you might actually want to do something numerical like this, where you compute these, like, you approximate these derivatives by, you know, something like what I'm showing right here, some small step away from where in each direction, and compute not the limit, but just that quotient, and say, well, that's pretty close to what the actual derivative is. And you can do that for all your directions, and you get an approximation of the gradient, but that's sort of silly because, as you've noticed so far, we just have linear functions, or we might have like some logs or some exponentials, and like those are like the only things we know how to differentiate for real. And yeah, so that's what we're using, because we can actually just analytically take their derivatives. Remember these guys in the era of long hair? Big rock. What's like in the 80s or 90s, you had the big hair bands, you know. Anyways, you're probably too young, but they were awesome. Yeah. So Newton and Leibniz, they were both big hair rockers. Yeah, like we can just, it turns out we can just like actually just take derivatives like immediately of like everything that we're ever going to work with. And if we introduce anything crazy, or if like your buddy wants to introduce something crazy, you smack his or her hand and you say, no, just use functions we can differentiate. Because otherwise you're going to have to resort to doing like a crazy estimation, and that's particularly slow. So yeah, we just use functions that we can differentiate by hand, or I don't mean by hand, but like analytically, so we can actually write down what the derivatives look like, and we can walk down their gradients. So, whoops, I skipped through that. Yeah, we always want to use analytic gradients, and that therefore means you've got to use functions that you can take derivatives of. And again, it's serious. Like if you see anybody using a function that just can't be differentiated easily, you just say no. There's no reason for that. Yeah, in practice, you always want to use the analytic gradient. You always want to like pre-compute these things, or have a software that pre-computes them for us, and that's where we're going to get to here in a second how that's done. But you might want to check every once in a while that you're doing things right with a numerical gradient. That's just checking. In fact, in your homework, there is some code for doing numerical gradients just to check that you've implemented the loss correctly. It's a nice way of checking yourself. But you only check yourself with it. This is not how you actually compute derivatives. Okay. So what is this algorithm that we keep referring to? It's something called gradient descent. So it's pretty simple. In its most plain vanilla form, it's exactly what I was just describing. you start with your, wherever you are in this 25 million dimensional space or whatever, and you compute a gradient, and you look at the negative of that, and you take some sort of step in that direction. So if I'm up here on the hill, and like here's my gradient, it's pointing back this way, I now have one more choice I have to make. How far to step in that direction? And how far you step could be really important. You know, if your surface is pretty much flat, you know, it's like kind of linear, then you can take very long steps and you'd still be going downhill. But if your surface is really, you know, curving all over the place, then you might not want to take a big long step, because then that, you know, that direction of going downhill isn't actually valid where you end up going. So this whole thing of step size is one of like the most important things when we're training these models of all. In fact, there is like many examples of like of models where you have to pick the right step size, or what ends up being called, when we get doing this more, the learning rate. You have to pick that correctly, or else you won't learn anything. If it's too big, you might just be taking steps and just kind of like really just randomly walking. It might just be as good as random search. If it's too small, then you're taking too small steps and you're not getting anywhere. It's taking way too long to go. And in fact, in the most sophisticated training of neural networks, the learning rate is actually not fixed, but it's on a schedule. That, you know, at each iteration of this, you might actually change the value of it depending on what's happening. And in fact, there's even more sophisticated ways of doing this that we'll talk about here really soon, probably the next week, about like modifications to gradient descent that keep around information from like the last time, something called momentum. So like you might keep some sort of running average of all the gradients that you've seen in the past, and combine that with what you see right now as a way of sort of like tempering yourself, that you don't just make wild choices. And you'll see too, we'll see this in this class and probably in some of the projects you take on. What happens almost always with training these really deep networks is that you'll start with like a learning rate, you know, that's like usually larger, and you're taking big steps at this point. And this usually gets you, what this has the effect of usually is getting you out someplace nice in this 25 million dimensional space, and then you drop the learning rate, and then that allows you to like take more precise steps and really go downhill and really find a low minimum wherever you are. But anyways, this whole I promise you, we're going to spend so much time talking about these things. It's going to feel so empirical and weird, but this is what we end up doing, but it's all based on something like this.
Yeah, considering this code, given a particular loss function at data, how do you determine the initial weight like? So that
yeah, so typically you randomly choose those, the weights, and I think at some point with some definitely with some of the models we will talk about certain ways of initializing that again you're drawing from distributions, the weights, so like you're sampling them, but it won't just be like uniform. There'll be a particular distribution to be sampling from because they'll preserve some sort of like statistics of the network. And that'll make more sense when we actually look at some of the examples. But yeah, but typically you just think of this as like randomly setting them. Like you don't know what they should be. Now you might think of like, you know, if you trained something before and you got to certain ways and that was low, you might want to start there again. That might be fine. But you also might want to try a totally different randomization because maybe that finds something different. I don't know. But like I just mentioned, typically, no matter where you start, you get to a minimum that's like equivalent to the other minima that you will find using other randomized weights. But that's typically what you do, is you just start with random weights. So when this thing starts off, you start with random weights. So the loss function describes your surface. That's like the derivatives. Or that's going to determine what derivatives you're taking. I should say what the derivatives look like when you take them. And the data determines which like what points you're taking this derivative. So one point that I haven't mentioned here, and it's not clear in this like pseudocode, is remember you have all this data. So you can evaluate all this data. So it's, it's your images from the CFAR10 or whatever it is. You have all this data. You can evaluate the derivative at each point, at each one of those data points, right? Like that's, so you get some weights, and now for any one of those points, I'm like somewhere, and now I can take the derivative there, and I get a gradient from that point of data. And then I can do it for another one, and another one, and another one. And they all will give you some sort of gradient, probably not the same, but they will likely be pointing in some generally similar direction, saying like, hey, losses is smaller over here. And what's done here in this evaluate gradient is you simply just take the average of all of those gradients. So you have a gradient for each point in your data set, and you calculate all those gradients, you take the average of those, and you say, okay, that's the direction I'm going to take when I take this step. Now that could be a problem. The approach is sound, but there's one problem in this, and that is you could have an enormous amount of data. So like ImageNet, which is like the one of the very standard data sets used for evaluating how good a particular convolutional network is, has well over 1 million images in it. You can't at every iteration like compute the gradient on all 1 million plus of those images and take the average. That would be really insane, actually. And there's ways of dealing with that we'll get to in just a second. So here is, this is actually not a very useful picture. Red is lower, so like we're looking like down on the surface. Red shows us what parts of the loss function are lower, and like we've been saying, like wherever you are, compute the gradient, you take a step in that direction. I was going to show somebody, maybe we'll come back to it in a second. So what I was just saying now is the following. You compute the derivative, the gradient, at every point in your data set, and then you take a mean, and that of all those, and that's the direction in which you go. But the problem is that you could have enormous data sets, and they would cost so much computation time to do all those gradients and then average them together. So a way that we deal with that is we do what's called stochastic gradient descent. And that sounds like really fancy, but all it means is that instead of using all your data, you just randomly sample a small batch or mini batch. The word batch or mini batch is used interchangeably here. I don't know why it was ever mini batch. It's weird. It's just like a batch. Anyways. You see, so mini batch, but people just say batch, I think. Yeah. But sometimes people say mini batch. So it's batch or mini batch. Anyways, you literally randomly sample a batch. The size will depend on a lot of things. Mostly it will depend on how many GPUs you have and how much memory all those GPUs represent together, and that will allow you to have a certain size data set, or size batch. But you literally sample at every iteration. You actually just say, okay, I'm not going to compute the gradient for all 1 million examples. I'm just going to compute it for 256 of them. So I randomly sample those. I just compute the gradients at those 256. I compute their average, and then I take a step. Now, what is the potential problem with that?
Maybe the data set you sampled might not give you the optimal parameters.
Okay, good. That's one.
Your data set's really big, so based on random points from all the data sets, you probably aren't going in like the perfectly steepest direction.
Yeah, exactly. It's like what you're saying here as well. So it's like, so remember that even with all the data, it's still an estimate of like the actual gradients that we should take, or the direction we should take. But this estimate is getting worse with smaller amounts of data. Yeah, so like the direction that we're going is not necessarily going to be the most optimal one. And in fact, with really small batches, it's guaranteed not to be the optimal one. And yet, we do this, and it was born out of necessity, first of all, just because you just can't, it just takes too long to, if you have a huge data set. However, it turns out that stochastic gradient descent has a really nice property that it adds to neural network training that is actually contributing, it's likely to be contributing to this phenomenon of always finding like equivalent minima. And what it is that you literally are, when you take a step with stochastic gradient descent, you can think of that like being like the correct gradient, and in like the most plain vanilla way of doing stochastic gradient descent, you can think of there as being like a distribution of the directions you could go. Think about like a Gaussian distribution centered at like the correct one, but then you actually take a step sampled from that like Gaussian distribution centered there. That property of having a little bit of additional randomness actually is itself a regularizer. So we talked about regularization, right? We talked about how it like smooths out the loss surface, or it like it conditions the weights to be a certain way. It turns out that the stochastic part of gradient descent is actually like conditioning the entire problem to give you this sort of behavior of equivalent minima. And it's not super well understood, although there's some great papers that sort of compare stochastic gradient descent to like a Langevin equation, if anybody's a physicist out there or seen this in something, Fokker-Planck equations. Anyways, it's these equations that they're dynamical equations of probability distributions. And yeah, so you can actually analyze these things, you can compute steady states, and you can see you can see this sort of equivalence, or like in pretty simple cases, you can sort of see this equivalence of things. Something that we're not going to touch on in this class, but the point of going through this is to say, don't think of stochastic gradient descent as like, oh, this is like, we're just too wimpy. Like someday it's going to get better because we're going to have like more memory and we can have the whole data set. We can compute the correct gradient. Actually, it would probably be worse if we could compute the whole gradient. Actually, things would probably be worse. We would get worse performing neural networks if we could compute the actual gradient every time. This notion of actually taking a somewhat random step in the right direction regularizes the problem, conditions it, provides an inductive bias. So it's like the kinds of solutions that we can possibly find using these algorithms, that's the inductive bias. It's actually way improved by doing this. So it did come out of necessity. I'm sure when it came out, like, the person who invented it was like, I don't know. Sorry. But actually it turned out to be really, really useful.
So is the point of gradient descent to find the global minimum then?
Well, you would love to.
Right.
You would love to, but because you're only using local information, you have no idea if you're going towards the global minimum.
Okay. Right.
Yeah.
But somehow through stochastic gradient, you're kind of finding...
You're finding a minimum, right? So like, I can go back to those pictures, but if you just think about there being two, I got the dot over here. Think about there being like a simple loss surface with say 2 minima, right? If I start here, my local information says to walk this direction to go downhill, and then I take a step of some length, I'm back on the lost surface, and I keep doing that, and I'll eventually just end up down here, and like I'll just keep bouncing around down here.
And that phenomenon you were explaining is finding two equivalent local minimum, not or global minimum.
Yeah.
Okay.
Yeah. That's right. They may be global. Who knows?
Yeah. Right.
They're very likely not to be global, but yeah. So if I start over here and I use local information, I'll end up over here. If I start over here and use local information, I'll end up over here. If I start right in the middle, stochastic gradient descent will pick a direction to go, but who knows? But what's interesting is that, like, again, this, you know, in this one-dimensional case, you know, it's like there's not a lot of interesting that's going to happen. But if I'm in a much higher dimensional case and I'm adding some randomness to the steps that I'm taking, it allows me to like explore the space like a random search. Like the one benefit of random search which is I don't get necessarily stuck in random or in local minimum always, although you eventually get to someplace. But it allows me to sort of explore the space a little bit better. And as a result, one of the likely results of this, it's not like proven, but like it seems empirically true. One of the likely results of this is that you're finding always equivalent minimum. I promise you will see this. This is just like a thing in doing deep learning. Yeah.
Equivalent minima.
Meaning the same.
What, like between runs or between?
Yeah. So it's the same. Like, imagine in 25 million dimensions. Like what I'm saying is there's likely tons and tons and tons of local minima, but they all have. I didn't draw it very well. They all have the same loss. Right, so I run my algorithm, I start from different initialization point, I get someplace, you know, I converged, and the loss that I have there is the same as if I had started someplace else and converged. It's not the same point. Remember, this corresponds to a W, you know, our set of weights, and so does this one over here. But the point is that they all have basically the same loss. Yeah?
Do the chances of like experiencing that phenomenon go down if your data set is smaller?
Yes. Yep. Yeah, definitely. I mean, yeah, definitely. It definitely goes down when you have far less weights. Like like your model has a lot less weights in it.
So I guess like if I'm trying to like classify cats, and if I use the absolute variance instead of stochastic, the template you showed like in the last lecture of a cat would be, I guess, more cat-like, which means like you won't be able to classify even less cat-like images, something like that.
Yeah. So one of the consequences of regularization is that it's better generalization, and that's what you're describing right now. Yeah. Yeah. Like what could happen if you don't use stochastic gradient? I'm actually not sure about this, but I think this is probably likely. Is if you don't use stochastic gradient descent, you're going to find a minimum. But it could be maybe like a sharper cat-like face or car-like thing, you know, which is maybe fine for your training set, but it won't generalize well to the test set. That's actually would be a good thing to have in the homework, but I don't have it in the homework. But if you're interested, you should actually try it. Like the data set's not too large; it's 50,000 or 50,000 samples, and actually have you downsample it to be smaller. Yeah, to like 10,000, 5,000. I think it's even 5,000. So, yeah, you could actually compute and just see the difference. But you'd be measuring something qualitative. Well, you could measure like the difference on the test set, and see, you know, you could test your generalization. You know, you'd see like the errors higher on the test set when you use plain vanilla or non-batch, non-stochastic gradients. So just gradient this one. But yeah, that'd be an interesting empirical test to do. Okay. Yeah. So what is actually happening here? So this is a cool demo that someone put together, Justin Johnson at Stanford, who I've taken a lot of stuff from. He did give me permission. Actually, he's not even translated anymore. He officially responded to my request and said, yes, that would be okay. So now it's official. When before it was simply transitive. Somebody else who had permission from him said I could use their notes, which were taken from him. So, transitive permission. Okay. Yeah. So the point here is this is something fun you could even play with if you wanted to. You could find it at this URL right here. But the point is you can do a whole lot here with like playing around with what happens at every step of this at every iteration of stochastic gradient descent. So what's happened here is like this is just like randomly initialized. There's a small data set of 9 points divided into 3 classes, 3 points in each one. So the weights are randomly chosen, and right now, like with the weights the way that they are, this is how it classifies the space. So it's like basically getting everything wrong except for like these 2 points right here, right? So the loss is going to be high here, and you can see what it is. So, so what you have is the loss computed, so scores for each of the 3 classes. So here are your 9 data points, scores for each of the classes, then the loss given your choice of loss function, which is down here. There's different ones you can choose from, and then the mean loss. And what you can see is, you can play around with this and you can see, so it says like a single parameter update right here. So I can choose my step size. Here's what W looks like right now, and my bias vector. But I can take a small step, and you can see like things just barely change. And I can take a much larger step, and you can see things change like a whole lot, right? So like if my steps are really large, like I kind of got into a good solution, but like I keep bouncing around it, right? This is a really simple problem. It figures it out pretty fast. But like every time I take one of these steps, like there's like some probability that I can get it all right, which is like right here. There's some probability that I step away from it. If I go back and just start with randomized, well, that's really bad parameters. And I take smaller steps, like really small steps, like this, you can see that like things are changing, but they're changing really slowly. Like really, really, really slowly. If I pick something sensible between 0.1-ish, then every time I take a step, I seem to be taking a step in a good direction, but I'm not also like just jumping over things and getting to the wrong, ending up in the wrong place. And so you can see how this is like kind of converging, and a little bit of random jumping around now that I'm down in one of the wells here, but it pretty much stays there, and I'm getting like equivalent values for the parameters every time. So anyways, this is just kind of nice, and it's just kind of nice to kind of build your intuition. I mean, obviously it's not like the data sets we're going to play with, but it's nice. You can add regularization strength to see how that changes things. Like if I have a really strong L2 regularization, you can see that this has a really hard time actually being the right classifier because we penalized those weights so much. But if I now weaken that like to 1, it allows it to, to find this. So like, you can see, let's see, what was the strength before? I think it was like 0.1 or something like that. So like now with the stronger one, it's having a little bit harder time, like maybe like dividing up strictly between, like putting a hyperplane like right between these points. But that's the point of regularization, is that you don't want to be super overfit to your training set. You want to be able to kind of like back away from that a bit so that, in case points aren't exactly the way that you have maybe a higher chance of getting them correctly. So, anyways, that's kind of fun. We'll just stop there. This is just on the side, depending on how much time we have. Next time we come back, we're going to do back propagation.